Today we're going to talk about optics. Optics is the scientific study of sight and the behavior of light, or the properties of transmission and deflection of other forms of radiation. And so today we're going to be talking about reflection, refraction. We won't get into polarization today, but we'll be talking about lights and E&M waves. So we know that light is EM waves. We talked about this a little bit last unit. And light comes in many forms. It's not just visible light, and so we know about there's gamma rays, microwaves, X-rays, all these kind of things out there. We remember that we have a term called amplitude that describes waves, and when we talk about light, amplitude is going to refer to its intensity, its brightness. It's going to describe that. And then when we talk about frequency, the frequency of the wave is going to determine its color or its category. And so you can kind of see that in the picture in this GIF to the right. We see that red has a less frequency. You see that those waves are further apart. They're less frequent than the violet, which those waves are more bunched together. They have shorter wavelengths, and so it has a higher frequency. And we also know that light is transverse waves, and so they propagate perpendicular to the direction they travel. We'll talk about what's actually propagating when we get a little bit further, but yeah, transverse waves. We need to know the electromagnetic spectrum. This is all the information we're going to actually need to know about it. We need to know the 7 different categories, and so I would go ahead and just sketch this on your paper. I draw an arrow and sketch all these words onto it. We need to know that, and we need to know them in order from higher frequency to lower frequency, or of course the reverse order. In this case, they're ordered from higher frequency to lower. Gamma ray is the highest frequency we can get. Radio wave is the lowest frequency on the spectrum. And as we move right, we get lower and lower frequencies. If we start on the right and move left, we're going to get higher frequencies, and we're also going to change our wavelength from longer to shorter. And so over here, we have higher frequency, as you can see, but we have shorter wavelengths. And they're inversely related because we know that we'll determine later the speed of light is constant, and we know that the velocity of a wave is equal to its lambda times its frequency. And so if light travels at all the same speed, then that means that these two are inversely proportional to each other, wavelength and frequency. So as frequency increases, lambda and wavelength decrease. We need to know the speed of light. I won't get too much into these stories, but if you want to look these up, they're pretty cool. They're not very important to know, though. Just turns out that we've known the speed of light for a while. We've had estimations all the way back that date to like the 1600s where we're estimating the speed of light. Now, that's not a very accurate estimation, but for its time, it's pretty good when we didn't have, a lot of technology to deal with. Later, when we got more technology, we were able to get a better estimation. This is pretty good, actually, compared to what the actual number is, and this is what we actually need to know for today. Speed of light in a vacuum is equal to 3 times 10 to the 8 meters per second. Okay? And we write it as C. C is the variable we use. Just kind of like when we use G is equal to 9.8, we use C as the speed of light. But that's in a vacuum. Okay, so that's the fastest it can move. But if we go into matter, light is going to slow down. Okay? Light's going to slow down, and its change in velocity, we want to give it a special name. So we have something called the index of refraction. And we're defining it as the ratio between the speed of light in a vacuum divided by speed of light in that material in medium. So this number is always going to be 1 or bigger because the vacuum is the fastest it can go. If it slows down, that means velocity is going to decrease. That means the number on bottom is always going to be smaller than the number on top. Therefore, we always get a number 1 or bigger. And so we can see that air really doesn't change the velocity a lot. Technically, the number is like 1.002 or something like that. I don't know. It's something along those lines. It's pretty small change. We don't really care. We can just round it to 1. Speed doesn't change that much, but in water changes a bit. Water slows down, and you can see that if you look into a glass of water and you put like a straw or something in it, we'll look at that later, it's going to bend the light a bit, and it's because the light slows down quite a bit. And so 1.33 is describing the ratio between the speed of light in the vacuum and the speed of light in that medium. So we can use this as we can do this in a problem. If n is 1.923 in zircon, we can calculate the speed of light in zircon. We have this equation. N is 1.923 here, and speed of light in a vacuum is 3 times 10 to the 8th. Therefore, our velocity, we just solve for it using some algebra, multiply a v on both sides, get v times 1.923 is equals to 3 times 10 to the 8th. And we can divide by 1.923, and we get 3 divided by 1.923. We get 1.56 times 10 to the 8th. Your calculator probably gave 156 with a bunch of numbers after it. Make sure you put in scientific notation. Don't write down that whole thing. That's pretty tedious. Shorthand it. Use scientific notation. Reflection. Light reflects. We know this. And the main thing we need to know is this term called rays. Light travels as a ray. It travels in straight paths. It travels as if it's, an arrow or like an object that moves in a straight line. It doesn't travel kind of like sound waves. Sound waves kind of travel outwards from a source. Light, it can do that. It can act like that sometimes, but for the most part, it's going to travel in rays. It travels in straight lines. Okay. And then when it hits a surface, it's going to be reflected off. And we have this intuitive law that it's going to be very intuitive to you, but we need to know some of the properties of it. We need to know what it means as definition. The angle of reflection equals the angle of incidence. As light comes in and hits a surface, it's going to reflect off at that same angle. But the angles we talk about when we talk about these incident angle and this reflected angle are the angles between the incident ray and the perpendicular. The perpendicular, if we have some sort of surface, we call the perpendicular a line perpendicular to it. Okay, this is our perpendicular. It's also called the normal. If an incident ray hits a surface, the angle we call the incident angle is the angle between the normal and the incident ray. And it's going to reflect off at an equal angle. We know these two angles are equal to each other. Now, if we have a less smooth surface, you can see over here, if the surface is less smooth, all the rays are still going to follow this pattern. And you can kind of see they kind of sketch in these normals, but just the normals are different directions. And because the normals are different directions, that means the light ends up being scattered. And so mirrors end up being pretty flat, pretty smooth. Light travels and reflects off pretty symmetrically everywhere. Okay, but unfortunately not everything's smooth, and so, well, fortunately actually, we wouldn't want everything to be chrome looking. And so because things are smooth, light bounces off in different directions. We get things that aren't, perfectly. But no matter what the object is, the light is going to reflect off, and it's going to reflect off at an angle equal to the angle it came in on. And this brings us to corner reflectors, which is just a very small point. I'll probably like maybe one question that's very just conceptual as recall on the test about corner reflectors. I usually know what a corner reflector is because they're very useful in life. If we have some sort of light that comes in, you can kind of see the properties here. If it comes in at some angle to that light, we know that this angle is going to be the same angle. And using our geometry, we know that this is 90 minus that angle, which means that that's 90 minus that angle. Again, you don't need to know this geometry, but just overall, you could see that if we add up all these angles, we're going to get 180 degrees. And so this light comes in, and it's going to reflect off at 180 degrees to the angle it came in. That means it's going to travel back parallel to the same direction it came from, which is pretty useful. Because if I get this reflector and I put a bunch of very, very small corner reflectors on there, if light hits this reflector on my bicycle, the lights are going to shoot back to the person that shined their light. That way, if a car's coming at me on the road one day, it's going to hit my reflector and it's going to bounce back towards that person. and they're going to be able to see me pretty clearly on the road. And we do the same thing on the moon. We put corner reflectors on the moon so we can shine lasers at them, and we can time how long the laser takes to return to us after we reflect them, and we can determine how far the moon is away from us, because it turns out the moon is actually drifting off ever so slightly over time. It's getting a little bit further away from us over time. We have refraction. Refraction refers to the thing earlier when I said that because the velocity changes as light goes into an object, the light bends as well, and we call this bending of light refraction. As light passes from one medium to another, it's going to change direction. And this is due to the speed of light changing as we change mediums. And it has an equation called Snell's law that defines this. N1 sine theta 1 is equal to N2 sine theta 2, where these ones correspond to one medium and these twos refer to the other medium. Note that this equation is symmetric. Both sides are exactly the same except for that are subscripts, and so it doesn't actually matter whether medium 1 is the original medium or not. They just need to be aligned. And so if this is the medium if this is your exiting medium, this needs to be your exit angle, right? Okay, and if this is your entrance medium, this should be your entrance angle. And you could even have it on the other side, but again, it's symmetric, so it doesn't really matter which side's which. And if we look at this image, we can see that as light's coming into a thicker medium, if medium 1 is air, and this is our water, we're entering a thicker medium, light ends up bending towards the it ends up bending towards the perpendicular. We have this perpendicular line here. We're going to call it the same thing. Our light's going to bend towards the normal, and if you really wanted to, you could use some math here, maybe even plot it as time goes on, or as you change into what happens to our angle. You could plot that, but you should know these facts in general. When the index of refraction is greater in the medium the light is entering, it's going to bend towards the perpendicular. And when the index of refraction is lesser in the medium the light is entering, it's going to bend away from the perpendicular. And here's a video link. If you can type in this link and watch it, it's a really good video. You only need to watch this. It's kind of a long video, but if you want to watch the rest of the video, it's pretty good. You only need to know 342 to 542 though. It's just a very good demonstration of why that change in speed is causing the light to bend towards or away from. And it makes it very intuitive, so you don't have to memorize these properties. You can just know these properties based on more intuition. We can practice a problem here, though. Let's say we find the index of refraction for medium 2, assuming medium 1 is air, and given that the incident angle is 30 degrees and the angle of refraction is 22 degrees. So let's write Snell's law. So index of refraction for medium 2, we're looking for this then. Medium 1 is air. We know the N of air. We had that earlier. N1 of air is 1. So we can put a 1 there. Times sine of our incident angle, our theta 1, is 30 degrees. We're looking for N2. And we know our refraction angle was 22 degrees. And so we can solve this. 1 times sine of 30 is just sine of 30. So we can even get rid of that. And if we divide by sine 22 on both sides, we get that N2 is equal to sine 30 divided by sine 22, which I believe gives us 1.335 about. So that is what the index of refraction of the second medium is, which is actually pretty close to water, so maybe this material is supposed to be water in this problem. I don't know. Doesn't matter. That's what our answer is. So if we look at this graph, though, let's say we're going the other way. Light would bend the same way if we're going the other way. So if we're approaching this, we know that light bends outwards. But what happens if we bring this further out? So let me erase this. What happens if instead we approached at a wider angle? Okay. That must mean that this is at an even wider angle. And eventually we get to a point where our angle is so wide that we hit this axis, right? At some point we had to hit there. We have to keep getting wider. And in fact, if we can go beyond that, there might be a point where what happens? Like, does it just come back? And that's actually the case. We have something called total internal reflection. As the incident angle increases, so does the angle of the reflected ray. Just so you know, whenever we shoot light towards the surface, some of the light actually is reflected back off. Even if you're changing mediums and most of the light's going through the medium and just being reflected, some of the light reflects back. But generally, most of it goes through. Sorry, some of these slides are messing me up. Okay. But if we increase this angle enough, like we saw before, we reach something called the critical angle. And at that critical angle, the light that's supposed to be exiting bends and is refracted at 90 degrees straight along the surface. Okay. While again, some of it's still reflected back. But if we pass that angle, if we go beyond this angle, all the light is reflected back into the original medium. We call it total internal reflection. If we go past the critical angle, like you see here, all the light is reflected back. Now, this only works when we're traveling towards a medium with an index of refraction less than the original medium. Only if we're going from something that's thicker to something thinner. Okay? It only works, for example, water to air. If we try to go air to water, there is no critical angle. No matter what angle, some of the water, the light won't be able to enter the water. But if going from water to air, if the light's in the water and it's shining towards the air, there is some sort of angle we can shine the light at that the light does not leave the water. Pretty cool. This is used in fiber optics a lot, if you've seen that. That's kind of how fiber optics work. If you've seen fiber optics, you see that they're kind of these clear tubes, and it might be a mystery of why the light never leaves the tubes, but it's because of total internal reflection. All the light, every time it hits the wall, it's at a pretty wide angle, and because of the pretty wide angle, it never actually leaves. Okay. And we can calculate this critical angle. Critical angle is equal to inverse sine of N2 over N1. Important note, this is your smaller n, and this is your bigger N. Granted, it matters, but granted, if you try the other way, if you put N2 as bigger on top, you can go ahead and try it in your calculator. If you did inverse sine of maybe like 3 divided by 1 instead of 1 divided by 3, it's going to give you an error. So you actually can't type in the opposite thing. So it'll fix it for you. If you see that, it just means you typed in your values wrong. I'll show you what I mean on this next slide. So let's calculate the critical angle. Let's say we have polystyrene, a type of plastic, surrounded by air. Let's find the index of refraction. If the index of refraction is 1.49, let's figure out what the critical angle is. So critical angle is equal to inverse sine of N2 over N1. N2 is generally the material we are entering. So in this case, it is air. We're trying to enter air at least. And so that means our N2 is 1, and our N1 is 1.49. And so the inverse of sine of 1 divided by 1.49. Make sure your calculator is in degrees today, otherwise you're going to get some bad numbers. You get 42.2 in degrees. Again, if you were like, okay, but how do you know what's 1 over 1.49 or 1.49 over 1? Again, try doing this. And you're going to see if you type that in, inverse sine of 1.49, you get an error. And it's because you're not allowed to do inverse sine functions. They can only take values between -1 and 1. Okay, you can't put any other number in there. And so it won't let you have values that this is about 1.49 is bigger than 1. And so it won't accept that value. And so it has at least a nice thing for you that you won't be able to forget that you have to put the smaller number on top. With that, that's all the notes for today. You should be able to complete the homework, the assignment. Have a good day.